And this is the first part of this one, and we are coming to the design part here. Okay, so before we start to design, is there any specific questions?
Sir, as of now, we don't have any questions. Sir, okay. We can continue the session for now, and we'll ask the questions at later.
Yeah, sure. Okay.
Okay, sir. Okay.
Yeah, this session requires much more time to explain, so that I've just gone through the theory in a faster way. So in the case of design of worm gears, there are steps like almost 8 to 9 steps we have to complete when compared to helical and bevel gears. The first section is like, obviously we have to select the material for any design. So in fact, we have given the reference to 0.7 page 234. In that one we can take for this one, and usually we use the material as worm is hardened steel and the worm wheel is phosphorus bronze. This is the usual material we'll be choosing. Suppose the material is not given, further we can take it from this page, like the 12.7 page 234, we can see that the material there. Next one is we will be finding the weaker part. Always we are designing the gear based on the weaker part. Here, although we are not following the same procedure as we are we are following the bevel gears as well as the helical gear. Here we will be taking the worm wheel as the weaker one. The reason is that when the worm wheel always slide over the worm, the structure is such a way that, and the helical angle is such a way that. So as a result of rubbing, there will be heating happens, overheating happens, and which leads to failure. So when heat happens, there will be changes in the strength of the material, and as well as the failure may happen. So obviously, the additional factor which has to compare with the we have to calculate in the case of worm wheel is the heat, which dissipated and generated. Then the third comes. So in the third, our second steps comes to we have to find the diameter. So first, we are classifying the problems based on center distance is known, and otherwise center distance is unknown. In the other cases, we were classifying with the case of diameters, which diameter is known, which diameter is unknown. In this case, center distance means the distance between two gears, that is worm as well as the worm wheel. The distance is known. So once the distance is given by the letter A. So we can calculate directly. If not given, we have to use this equation, that is power will be given, how much power we have to transmit. Then from this I dash is the transmission ratio, that is N1 by N2. From this we have to calculate what is A. Once the A is calculated, then further we have to go for other calculations. Then comes to the module, where the module equation is F equal to sigma D CVP YM, where we can see in 12.53 page 223. And the parameters here we can see is sigma D mostly will be given. If not, we have to take it from the data book. Then we can see the CV, that is velocity factor, then B phase width, and Y is the form factor, and M is the module. From this one, M can be calculated. What is M? So here Y is changed to pi M. That's sort of difference here. All these factors can be used, and in the problem in a problematic description, I will show you how it can be done. And then comes to the finding the lead angle, where I have explained what is lead angle. So you can see that when we take a plane that is normal to the axis of this worm, as well as when we take a tangent from the worm, there will be angle called, we use this angle gamma as the lead angle. We have to find out the lead angle, tan gamma is equal to mz by d1. Then we have to, as we have already done in other gear designs, we have to use the dynamic tooth load. We have to find out what is the force that is occurring during running. When the gears are rotating together, there will be additional force will be acting because of different factors coming into being. So even if a friction is there, obviously friction should be there, and forces are coming into the scenario, and as a result, and the thrust forces, many forces are coming into this one. A dynamic tooth load comes here, so that should be calculated. Then second one is here to calculate the wear tooth load. The wear tooth load, in fact, what is meant by wear tooth load is the maximal load at which the wear can take place. So obviously, if the dynamic load is equal to wear load, that means it's not in a safe condition. However, we can run it for some time. The major condition is the wear load should be greater than dynamic load. Fs is represented by dynamic load. So as a result, if the wear load is greater than dynamic load, then even though some force is extra added to that without apart from designing because of the external behavior, the gear will not wear. So that is the major thing here. Then comes to find the efficiency, and we have to calculate the efficiency based on this equation. So the major is that worm drives the worm gear. Here worm gear drives the worm. So in two cases, in the data book is given and two equations, we have to use that. And all the parameters required from theta can be calculated from this one. And that's the rubbing velocity, then our friction. So all these things can be calculated here. And then the final comes to the heat generator. In fact, the heat generator means like as there is a rubbing happening between the worm and the worm. As a result of rubbing, in fact, the heat is generated, and this heat should be dissipated, or else what happens, the metal is getting highly heated, and finally the failure occurs because of this reason. So this is the equation we can use in this one, and Fn equal to Ft by cos alpha, cos gamma, cos alpha. This from derivation I haven't seen in the data book, the Mahadevan. I hope it has to be understood and learned this equation for just calculating heat generator. Then heat dissipated is given by this equation. So dissipated, in fact, is maybe by a natural conversion, or maybe if the forced conversion is there, obviously that the heat will be dissipating. However, what we are doing is like we are comparing heat dissipated and heat generated. If heat dissipated is greater than heat generated, obviously artificial cooling is not necessary, because heat is rejecting out is greater than generated. So it's in a cool condition. In the other case, artificial cooling is necessary and a fan should also be provided. So this comes to the demonstrative problem. So we come to demonstrative problem. This is a problem, design a worm gear drive. So it has to transmit 2 kilowatt of power at 1000 RPM. The speed ratio is given as 20 and center distance is 200 millimeter. Assume number of teeth on the worm wheel is 40 and number of starts on the worm to be 2. Assume hardened steel and phosphorus bonds. Obviously, the material is already given, sigma D. That is, this is the permissible static stress that is given. Then check the gear for the standpoint of strength and wear. If load stress factor K is equal to 0.69 megapascal, and if the amount of heat generated is 1.7 kilowatt, check whether artificial cooling is necessary or not for a temperature rise of 40 degrees. So there is a temperature rise is given. In fact, we have to check whether artificial cooling is needed or not. So that is the major thing. So I just listed out all the given parameters here. And first, and what design for strength and wear, that is the thing. And here, this factor is like temperature T2 minus, that is rising temperature is 40 degrees. So when running, 40 degrees is generating, heat is generating us is 40 degrees centigrade. That's just temperature. So temperature and heat is quite different. Okay, we'll come to that. And it comes to this first part, like we have to find the material selection. So as I see in that page number 234, there is a material has to be selected for this one. However, the case already the material is given, so we don't want to select, or else we have to just take this one and we can find out the sigma D from the material if not given. Here the sigma D already given. And second part is to identify the weaker gear. Obviously, I told the worm gear is the weaker part because of the generation and rubbing happens over that one. Parameters I'll carry over this to this one. The third step is second step is like finding diameters. We have to find the diameters of both the gears. So in fact, you can see in the case of this one, force speed reduces with integral worms. The AGMA recommends a mean pitch worm diameter. So this is the worm diameter, which is taken as the D1. So using the equations, A is the center distance, which is already given. From this one, I have taken A, and we calculate D1 equal to 75 mm. In the case, we have to calculate D2, where the center distance is given using the equation. We know what is A, we know what is D, and D2 can be calculated. Now the first parameter, like diameters of the both worm and worm wheel, has been calculated. Next, we have to calculate the module. In fact, this is like a little bit lengthy. However, we have to take care of this one while calculating. So we can see that one in the third step. The permissible tooth load according to Lewis equation is because the module will be calculating based on the Lewis equation, that is the static case. So because we have to mesh together, initially the meshing happens in the static case, then only the dynamic force coming to being, where Buckingham theorem will be further following. So Ft equal to, there is an equation. From this we can see a module here. So sigma T is already given here. Sigma T already we have a 55 megapascal, and then we have a CV. CV value should be find out, and so CV can be find out from this equation, that is 6.1 by 6.1 plus V, where we should find out from here. So you can see V is equal to, in this equation, V is equal to, because we are designing for the gear, worm gear, we are using D2 and 2. We are not going D1 and 1 because driver is pinion and driven is worm wheel. So from this, velocity is calculated, and substituting this one, in this figure, we'll get CV. So we already find CV, sigma D, and unknown is B and Y. Then we have to further go for B and Y. Remember that N2 is required in calculating V, where N2 can be calculated from the gear ratio. So this we have to use some more common sense how to calculate all the things by relating. It may not be always same questions, but we should know that I equal to N1 by N2 is equal to Z2 by Z1. So all these things should be, we should have now D1 by D2 by D1 should be in our mind. Then comes the second part is like as I told, like sigma D already calculated, CV already calculated. We have to calculate B and Y. Well, we are coming to calculate the Y. So okay, here we calculate the FT. FT is calculating with the equation FT equal to 2 MTE by D2, where MT is equal to MT into KL. There is a factor called KL. So we have to calculate what is KL. We come to page number 248. There is a KL, but it's not specified anything. So we are taking this one as a steady load turbine plow. It's a steady load. We are choosing this one to make our calculation easier. So we are taking the steady load. KL is taken as steady load. MT is calculated, and MT is I can see MT is calculated, and 2 MT by D2 we will get what is FT. So once we get FT, this parameter is also found out. And next comes we have to calculate the Y to come. So whatever I have found out, always I'm updating here. So all the things which I already previously found, updating here. So we have calculated N2, CV, V2, everything is updated. Then we have to calculate what is the factor called Y. So in fact, we know capital Y equal to pi into NY. So before that, we have to calculate what is this Lewis form factor. For that one, first we have to take Z1 equal to, this is the number of threads. 2 threads is having. So we'll go into this one and see single and double threads. In the page number 244, single and double threads. We have to get the pressure angle. The pressure angle alpha. And when we get the alpha, we have taken from this table 12.28, that is alpha is equal to 14.5. We get that. And we are choosing 14.5, and Lewis factor Y is found from this. And this Y is like substituted here pi into Y, and we will be substituting Y. So like we can get Y equal to pi into Y. There is 0.1. We get this one. So we have calculated the form factor. And finally, only thing is that base width. And obviously, you can see somewhere here. We can get it from a different table. However, the reason behind this is we don't know the pressure angle, and exact Z1 equal to 2 we don't have. We don't have a measurement that is given in the table. So as a result, only we have gone through this way. If given directly, obviously we can go through that as well. Then finally we are calculating B, where B can be calculated B equal to A power by 2. Direct equation and calculate. Now substitute and find the module. We'll calculate the module. So I'm updating in the next, that is what is module. Next comes to the module is 2.88 calculation, and it has to be standardized from the table 229. That's page number 229 table 12.2. We can see that module is 3. That is we are standardized, and I have written as module may be used in as for the calculations. Then next one we have to calculate the lead angle. So lead angle having the equation we can use in the equation 221. In this one D1 equal to Z1 M2 by tan gamma. So all these are we are selecting depend upon the given equation, what the parameters given in the question that's available. If not available, obviously we have to choose a different equations according to the data given. So here we are using that one, and from we have to calculate what is gamma. So gamma is equal to, we can calculate the tan inverse is Z1 M2 by D1. So, and gamma is 4.57 degree. The next one is the dynamic tooth load, and dynamic tooth load is represented here as the Fs equal to sigma d bym, and then all the parameters are already given here in the sigma d. For this one is given, and it's for B. We have calculated B, and Y calculated M. Everything is calculated. So finally we can calculate the dynamic load. Now we have to calculate the wear load. So wear load equal to D2 BK. So in fact, K is a factor which is already given in the question. So as a result, we don't have to go for that one. K is already given, or else we have to find out from the table 12.30 if not given. As is given, we are taking directly here. Then D2 is already given. We know what is B. and we know K. So from this one, we can calculate. And finally, this is the conclusion here. So once we calculate 12.33, so we say FW, that a wear load, is greater than dynamic load. Now, when we divide, you can see 12330 by 28516, almost 4.3. That is the factor of safety is 4.3. Even though some external force act on the gear and increase the dynamic load, what happens? It can increase up to 4.3 times what's the load acting right now. So it's a very safe condition. So we can move with the further designing. Next one, the efficiency. So efficiency, the equation is given our efficiency when the worm drives the worm wheel. That is equal to eta equal to cos theta minus mu tan gamma by cos theta plus mu cot gamma. So from this one, we have to calculate what is tan theta, or theta should be known as an unknown here. Tan theta is equal to tan alpha cos y from the page number 224. And we can calculate what is theta, substitute theta, and also gamma is already. We have to find out what is mu. So for calculating the mu or the friction coefficient, you can see we can use the equation. The reason is that one, the greater speed than 2.75, this equation should be used. So as we all see the velocity, when we see the velocity, you can see it's like we have calculated the velocity v equal to pi dn by 60. So in this case, okay, before that I'll just have a parameter y is selected. Okay, vr is equal to pi dn by 60. We have found out 3.94 second. Again, we are calculating the velocity here, v pi dn by 1000, where the velocity of the pinion. So it is 3.93, which is greater than 2.75. As a result, we are using this equation. If it is less than, you have to go for this equation. So v equal to, we are finding and finding the factor. Now mu equal to 0.0375. Now all the parameters I hope we are calculated for the efficiency. Now substituting, and we are finding efficiency equal to 66.92. So remember that already I have just shown you, that is usually that comes when gear have efficiency from 50 to 90. So this comes in between 66.92. Next part is finding heat generator. So heat generator, usually we will be finding the equation in the page number 227, this one. However, heat generator is already given in our parameters, so we don't want to calculate this heat generator. And so here there is a Fn. Fn is factories. Fn is a normal force to the tooth surface. So Fn is equal to Ft by cos gamma cos alpha. This is calculated from the derivation, and I haven't seen anywhere in the data book. Obviously, we have to just know about this one, or we have to derive from this equation. There is a diagrammatical equation where we have to calculate from this one, force analysis. So heat generator is already given, and then we can go for heat dissipator. So heat dissipator, we have to find out the equation for heat dissipator, and then that should be solved. Now we can see that one heat dissipator, another equation for the heat to be is equal to Q equal to 0.407 by this equation. The reason why we are using this equation is there is a factor called T2 minus T1, where in the question is asked to find out for temperature, change in temperature, T2 minus T1 equal to 40 degrees. So that we are using the equation. Temperature is not given. This equation can be used where this is an approximate calculation without temperature. Now there are factors called AG and AW. AG you can see here, this same the page number. AG equal to pi by 4 d square area of the worm gear, and where AW is equal to projector area of the worm, that is LW into D1. Where we have to calculate what is LW, we can come to 243 page number, where that is LW is the phase length is given as 14.4 plus 0.063Z1 into M. So this we are taken for single and double threads. Our thread is a double thread. When it's a triple thread, we have to calculate this one. However, the equation is same for both. Now calculating all the values here, that is we are getting AG, AW, LW, and substituting, we get what is the heat dissipator equal to 1402.845. Dissipator is 1402.85 is less than heat generator, that is 1700 kilowatts, which is already given 1.7 kilowatts. So sorry, 1000 is wrong, is 1700 watts. So this in between, as you say, QD is less than QG. As a result, what happens is that the dissipated is less than generated. So more heat is generating all the time. As a result, we have to give some artificial cooling. Artificial cooling should be given for this one. And that's the problem we'll be solving for this kind of things. And I have used the references here. And thank you for this section. And maybe if you have some questions, you can ask. And I have to show a software demo where you can just work out if you're interested.
Thank you, sir. So we have some questions.
Yeah, sure.
Sir, I'll read it off for you.
Yeah.
So the first one is, as wear and tear is high for this worm gear,
Yeah.
is there a special kind of lubrication needed? If yes, please explain.
Yes, obviously lubrication is usually we'll be using the lubrication. But however, as the point of in the real design, we'll be using this one. This is as per the academic point of view, where the lubrication layer is not considered or sliding layer is not considered in this case. So whatever is like when the lubrication comes into the factors has to be taken, like the viscosity of the lubricant and the reduction in the friction coefficient. Everything has to be calculated, or we can take the friction coefficient and reduce it to the lubricating things. So that happens in not in academic point of view, which is very tedious and you cannot complete within that hours of examination. The calculation cannot be complete. That's why reason I think academics are not included in this.
Okay, sir. So another question is,
The worm wheel. If needed, we have to change the design.
okay, so sir, another question is there any mathematical relation between lead angle and helix angle?
Okay. So as of now, I have improved, but we have to take it from the theory, like to the slide here. Okay, you can see this is the lead angle, this is the helix angle. This is related like this. If you just add together, what will be the relation? That is gamma plus psi, or usually beta is used in data book. So gamma plus beta equal to 90 degrees. So we can use that relation if needed.
Okay, sir. Okay.
Audio is, I cannot hear. I cannot.
Can you hear? Oh, okay. So there are two equations for calculating efficiency of worm gear. Will it be specified in the question which is the driver or the driven part?
So like since I told like we are designing this one as that you are taking the worm wheel as the weaker part, means worm wheel will be always a driven one and worm is the driving one. So that is the usually weak case for the academics. In fact, we are not going for the other case. So that for some reversing actions or to brake when required, we'll be using that type of designs. So in fact, you can go with this one only, that worm is the driver and the other worm wheel is the driver. So obviously there won't be any confusion in taking design part.
Okay, sir. So another one is, so what are the areas of applications where worm gears are used, and is there any areas where only worm gears can be used, even though the efficiency is very low?
Okay. So the first of all, you have to understand that the major thing is like the worm gears are majorly used for velocity reduction. So that's why I told you, like, when we take an electric motor, it can run all over 2000 RPM. For example, I can take a machinery case. For example, some case of a machinery where rollers are running. To have in Jindal Steels Industries, we can see the two rollers are running. The steel is in between that one, so that it can flatten more. So the major reason the velocity should be well controlled, or else there will not be flattening of the steel happens. Also, the rollers will get damaged. However, in the case of an electric motor, it will run at 2000 RPM or like that way. As a result, what happens is that if 2000 RPM the rollers are running, what happens? The rollers will get damaged, the steel will get damaged, the product will not get. So when we are applying a worm gear, the major advantages is that it reduces in a single step. The single turn itself, what happens is that 3000 RPM will be reduced to 50 RPM. And that depends upon the ratio, how we are just how we are designing it. Then second one is that the space is much less required. The machine will not be bulky. As like in the Varghese, we have to use the gear trains. That is many gears combination to reduce this. Also, major other application we can see that one in the elevators, because it will not rotate back. They did have a braking mechanism. So all these things can be used as.
Okay, sir. Another question is, what type of worm gears are used in indexing mechanisms in gear cutting?
Can you repeat the question? I didn't hear it clearly.
Okay, sir. So what type of worm gears are used in indexing mechanisms in gear cutting?
Okay. So what is the need of using a worm gear in indexing cutting? It's if the efficiency, when we compare the efficiency and high load to be transferred, we'll be using the worm gears usually. And indexing cutting, in fact, I don't know exactly what type of worm gears are using in there. But usually I haven't seen the worm gears. When there is a speed reduction required and efficiency high, we can use such things. I hope that is the reason that you have to find with the companies what type of they are using.
Okay, so I think the question is clear. Sir, again, one more question is there. Sir, is there any derivation for the normal force equation function?
Okay, normal force equation function means can you make more clear on that one?
Sir, I'll ask him to make it clear. Sir, another question is, one more question is here, sir. So what about the metallurgy of worm gear, and what are the common materials which are used to make worm gear?
No, this as per the academics, as we can see that you see the bronze, can use a bronze and phosphor gear bronze. Steel can be used for this one. So this depend upon you can see all the materials here. Usually, what is your requirement? How much force we have to transfer? So we will be selecting sigma d based on the material. That is, we are always we will be just comparing the static with the force which already calculated. If the static stress, if the calculator is greater than static stress, obviously that will fail. So what is your application and what is the power to be transmitted depend upon the material has to be selected based on the sigma d values. And that doesn't mean we cannot, it's not restricted. However, there is restriction in the manufacturing methods. If it requires, when we have to make the worm wheel, specific manufacturing methods are required. So in that cases, obviously, we have to limit the materials, as per easy manufacturing.
Okay, sir. So the last question was, is there any derivations for the normal force equation function?
Okay, again the same question. So,
this is a derivation function, sir. Normal force equation derivation function.
If I want to refer that one, if there is such things is there, and maybe I hope. Okay, let's see. So I hope is asking something about this force, that is this normal force derivation function, like a normal force is there, and the derivation for this function or something. Or else I can contact there's an email.
Okay, sir. Okay, sir. We'll collect the question and we'll collect the question and mail it to you. We can answer later.
Yeah.
So we'll go to the last question. Sir, what are the applications of double, triple threaded and 4-threaded worms?
Yeah, that's I told the major reason or the major idea behind creating such forms is that one, like when we need require a precise movement, like the pitch movement is very precise, as well as when we have to just transfer high amount of power, that is more number of threads are coming into contact with this one. In that cases we'll be using. So generally that is costlier when you use. So when we make a gear, we have to take care of the cost with other applications. That is whether that worth in the business. If so, we can go for that. So that such applications are like precise and specific applications will be only going for such things. In normal case, as I have seen the robotics and everything, they are using a single one. Since that much, whenever precision required, we go for that.
Okay, sir. Okay. With that, we are coming to the end of the session, sir.
Yeah, just a second. Like I have to show. I have to show one more thing here.
Okay, sir. Wait.
Okay. So. Okay. So I hope the screen is visible. This is Autodesk Inventor. So if you are passionate enough, like we can see these things without just designing in these cases. Like we can go to assembly. That is we can go to file new assembly in the Autodesk Inventor. Once we come to the assembly, we can go to design in this part, and many components you can see over here. And apart from, I'm just showing you worm gear. So we can take the worm gear. So like so already have taken the worm gear. Okay, this when we take the worm gear, you can see the design part here. So design part having many components. As I said, the center distance, you can change the center distance, or can choose the center distance. And there is a calculation part here. I'm not showing any how it's doing, because it should be a different session to do that. So all the things you can work out on this one if you require. And remember that one exact what are the calculation what we are done already may not be obtained from here, because this is considering a practical way of doing these things. We are calculating atom clearance, root fills, and as you said, lubrications if required. All the things are calculating materials and Poisson's ratio, worm material coefficient. All things are calculating, and finally we are designing this gear, exact gear. So if you're interested, like we can go to Autodesk Inventor, which is an actually educational package which are always assisting education, and we can design. Also, moreover, there is like another called the ANSYS package here. So in fact, this can also be used to analyze this one, and you can you can use static structural to learn very easily. This can be learned. So static structural part can be used for easy learning. And if you require for some movements and everything, then obviously we can go to the explicit dynamics session. And, okay. You can see that as Dyna, explicit dynamics is there. So you can take this one and learn like this way, better to have more idea on the design part. This can assist you in learning. So with that, I just completed my classes.
Okay, sir. It is really happy that you use all efforts to clear all doubts, and that was a wonderful session, sir. And it was well explained too. And we hope that the session was helpful to each one of our attendees.
Yes.
And if anyone of you want to view this session again, you can visit our YouTube channel. ASAP official channel is there near YouTube. You can visit that. So thank you, sir. And all who took their time to attend this session. Thank you so much.